Okay, this is our last discussion. Maybe I will give some quick recap and overview on what we have done, and maybe something that I'm missing before. So we first start with the sequence. That is the same sequence that you have learned before. It is a list of numbers that are in order, arranged. Okay, you can write in something like this, and of course you can also take the sequence to be in some pattern or in some formulations that you can call the formulations in general in terms of AN. Okay, and it can be any formula that you can think about it. And then you can also have some formula that is not really restricted with the pattern, okay, like Fibonacci sequence, right? And also other several formula. Okay. And then by looking at the sequence, if for example we have this n over n plus 1, and we are looking when n is getting bigger, getting larger and larger and larger, what will happen with the number? Here, the number is getting close to 1. So it seems that because of this property, we can approach this sequence with limit, right? That's our conclusion last time. So we can take the limit, okay, as the n or the integer getting larger, then it is getting to be close to some finite number. We call maybe L or any number that can be input, right? And then if we are looking at the limit, if we can find the value of the limit, we can say that the limit exists, or we can say in our chapter 11, we say it converges or convergent. Okay? If it doesn't exist, or it is diverge or divergent, or if you focus on the words, converge means in English it's going to be focused to one direction, or diverge is going to spread out, which means that it can have many possibilities, which it means the limit itself doesn't exist. Okay. And then we can see some of the visuals, how the limit looks like in terms of the sequence. We can have this, like the left one. We can have some random sequence at the first, but later when you increase n, maybe it will have some certain value, and of course it has limit, and we can say that is convergent. Okay. Like this one, also the right one, maybe it has some oscillations, like going up, going down, going up, going down, but later when you increase n, maybe at a certain point it will reach some value which is finite value L, and we can say also this is converged. Okay. And also this is just a recap on a limit law, the same law that we applied in the last semester. And also we can apply the squeeze theorem because of the limit. Okay. If we can make sure that we have three sequence or three limit sequence, and we know all the middle one is in between of A and C, we can make sure of that, then we can apply the squeeze theorem. Okay. And we know that limit of AN and limit of CN, if both of that limit the same value, then the middle one should be the same value as well. Okay, so and also you can use L'Hopital rule because that is also limit. Whenever you find 0 over 0 situations, okay. So whenever you find indeterminate form in limit, in our case, you can always apply L'Hopital rule. Okay. Okay. I think number 6 is also important. It's using the absolute value. Okay. So if you can have the absolute value, if the limit itself is 0, then the limit of the sequence also 0. Okay. Okay, that's just my recap summary. And we have done until here. That is, if we have limit of the sequence is going to be at some L, and then if the functions, they are continuous at the same value L, then we can say that the limit of functions of the sequence, then it should be functions of L as well. Okay. Okay. Now I know that I think in previous semester I didn't really get into the precise definition of limit. Okay. But I think I can give you some enlightenment on what the precise definition is, okay, according to this sequence. Okay. But it should be similar with the general precise definition of limit. Okay. Okay, let's say sequence n has limit L. If for every epsilon greater 0, there will be corresponding integer n such that, let me change the color, if n, the small n greater than the capital N, then the difference between these two will be less than epsilon. So what does this say is, actually in general, precise definitions tells you that if you have the limit, like for example, let me take you to these visuals to make it easy to understand. Let me just make a general definitions first. Let's say we have some removable point. Okay, we say that the functions at x equal a is undefined, right? Because there is discontinuity. Okay, but we can say the limit. We say the limit exists, right? Because we can go from the left, go from the right. Okay, but if we are going to say, like maybe if this is 1, maybe we can say that nearby 1 is maybe 1.00000 something, right? Maybe nearby the other left is maybe 0.99999 something. Like there is like small gap that if we compute with limit, we ignore that gap, right? Because limit is saying that this is, we can say limit as a closed, how to say that? Maybe if I write concept of how close, you can say close value something, anything that you can put into a functions and a value, you can use limit and you can ignore the small gap in between, and you say with the limit concept you can ignore that small gap. But of course in math or in calculus we need to know how close it is, like how small it is. And usually in precise definition of limit, we are going to have, we say that there will be a small distance here. Okay, let me just draw here. Okay, there is a small distance that we say that this will be a delta. And because of this delta, So you will have A plus delta and A minus delta on the left, right? And because of this delta, it will also give you difference on the L as well. Okay, so because of this delta, we will have also epsilon, the distance in L. So delta and epsilon is a small distance, okay? Small distance. Now, this epsilon is the one that we are talking in here, this one. Okay, the same concept of epsilon, which means that we are going to define how small the epsilon is. Okay. Okay. Now, if we draw the in sequence in here, let me draw first. Yeah. If we draw, and then maybe we can say okay, if we plot some sequence, so A1, A2, A3, plot on number line. And let's say our numbers will be start from 0, A1, but A2 I will write here, and then A3 will be back to here, and A4 is going to be here, and then A5, A6, and then A7, maybe a little bit going to be here. And then A8. So what I want to show you is this is the sequence going forward and backward. Like they have some kind of order. So from A1 to A2, and then going back here, and going forward, going back, going forward, and then going back. And then probably A9 is here. So the idea is, I just want to show you that this sequence will getting closer to some L. Maybe L will be here. Maybe L will be at this point here, and we can write down some value in between those L, small gap value, that this will be A n plus 1, and maybe this is A n plus 2. And then the small gap, maybe here to here. This will be, maybe I will write a little bit going to be left here. This is going to be here. And this will be L minus epsilon. This will be L plus epsilon. So if you look here, the interval between L minus epsilon and L plus epsilon, okay. So in between this interval, there exists some integer that all terms of the sequence from an plus 1 onward must lie on the interval. Okay, perhaps it's not really clear if the number line. Let me just illustrate with another graph. Okay, maybe just a Cartesian. Maybe it's much bit better. Well, let's say this is n, and this is n. Okay, let's start from 1, 2, 3, 4. Okay. And maybe L is around here. Maybe the first one, second, third. Okay. I think until here. And then it will be getting the same value at the end. Okay, let me draw the line L. And let me draw another one. Okay, now this will be y equal L plus epsilon. This will be y equal L minus epsilon. Let's just set some integer that is here. Okay. So, which means that there will be some integer that we can set up in any interval between the epsilon that we have, and it must lie between the interval of the L minus epsilon and L plus epsilon. Okay. But in other words, what this precise definition means is whenever or how big your n, it will always be on the interval between this epsilon. This is just to show you that the epsilon that we are illustrating here is really small. Although we are drawing like this, but you need to consider that and imagine that the distance of L to the epsilon or to the plus epsilon and minus epsilon, it should be really, really small. So that it means that the integer itself should be lie on this interval. Okay. So whenever you switch the n, okay, and as your n is greater than integer, and it should be having this small epsilon. This is just to show or to symbolize that the distance is really small, okay? Because the limit, is we are using the limit concept, that is we ignore that small number that might be encountered, then we need to define what is those small numbers, and in our case this is the epsilon. If you want to look more onto the general definition on a precise definition, this means that at every delta or at every distance here, that maybe we can take this, if this is A, We are just looking at every distance between this x and a, there will be some delta, in which that delta will be also, when you put the delta inside this, it will also prove that it's less than m. Okay. This is just to symbolize, okay? And of course, in this sequence, that problem might happen. Okay, we can write also here another definitions. If we have limit as n approach infinity of sequence, if this is resulting in infinity, this means, okay, for every positive number m, I will define m later, there is integer n such that if this greater than this integer n, then the sequence itself will be greater than m. Now this is analogous with the limit, that is if we have the negative infinity, means it will be smaller. Yeah, so if you see any symbols in the precise definitions, like m and or in the original one it's called the delta and epsilon, it means it can be for any number that you can think that if you put the number and you can see that if those numbers is less than the sequence, then the sequence will go increasing without any restrictions. Okay, if you see the relations. Okay? When you increase the integer, you will have some sequence that always getting increased. Okay, so you can say that this is you can think that the sequence is unbound. Okay, so whenever m you put, the sequence is always greater, always greater, and it seems that it will be increasing over and over. And you can say that it's diverged or it's unbound, okay? or diverged. Maybe diverged is better way to say it. And again, you don't really need to know how much m, but you know that every number that inside is basically getting increased. Okay, from here, I will go to the next slide, or if you want to take notes, you can take notes first. Let me go to the next slide. Now, if we have the limit as n approaching infinity of r with power of n. And the question is how or what values of r is the sequence converges. Okay, now we can think this as in the limit in chapter 2, I think, limit as x approaching infinity of some exponential function b with power of x. This will be infinite for b is positive or greater 1, and it will be 0 for 0 less than b less than 1. Okay. Now the same thing happened in our sequence. That is, if we have this limit, this will be equal to infinity if the r is greater than 1, and it will be equal 0 if the r is in between 0 and 1, or in terms of fraction. I think you can review the infinite limit on the chapter 2. Okay, if we look on the -1 less than r less than 0, if we took this interval, okay, then if we take the absolute value, then this will be turns out. And so by the limit law that we have, we can say that limit as n approaching infinity of the absolute value of r with power of n, this will be equal with the limit, which is 0. And therefore, the limit of r with power of n will be also 0. And if r is less equal -1, then the sequence r will be diverged. So the sequence is convergent if So it will be convergent if between this interval here, or we can say it's from this. And how about the number for the convergent? How about the value? Then we can say the value it can be 0, it can be 1, depends on the interval as well. The value can be think as a limit of n 1 with power of n, and limit as n approach infinity 0 with power of n. So if r is equal 1, then the limit value will be also equal 1. Okay, now monotonic and bounded sequence. Okay, first, if you see the name or the terms, monotonic and bounded. Of course, bounded, you know what it means. Bound means, if we say unbound, which means it has no restrictions. Bounded means it has restriction, which means if we are talking in terms of limit, we will know that the bounded means that it will have some value that is going to be close to, right? If we talk in limit. Monotone or monotonic, it means mono means 1, okay, 1. So it can be, you can think like you have limit and then increase, right? Or decrease the limit, right? In sequence. The number on the sequence you can arrange, and maybe you see that the pattern become increasing or the pattern become decreasing, okay? So increasing or decreasing, that's called monotonic sequence, okay? If you have both and constantly it's changing without any behavior that it's approaching some number, it's always oscillating like sine or cosine, which means it's not monotonic. It has increasing and decreasing, okay? And it won't stop, right? But when you have some oscillation, but maybe it will have some time that maybe it will reach some constant value, then we say also it might be monotonic at some interval, okay? So let me write, okay? So sequence, it can be increasing, right? Or decreasing, right? We call this sequence increasing, okay? Increasing means if the an is less than an plus 1, of course, right? The next term should be higher, right? The next term, the plus 1 should be higher. This is for all n equal greater 1. So we start from n equal 1 and then it start increasing. So A1 is less, A2 is less, A3 is less. Okay. And it's called decreasing if an is greater than an plus 1. we say that this will be okay. And sequence called monotonic if it is either increasing or decreasing. So now, from this definition, to help you to configure whether the limit has value or not, we can look on the behavior of limit itself, or the sequence itself. Is it increasing or decreasing? Okay. So we can look on the an and an plus 1. Okay. So we can observe or analyze from that point of view. Okay. Okay. Now, if we look on one sequence, for example, the sequence is an equal 3 over n plus 5. Of course, I think this is quite simple. We can look the an, and maybe we can take the an plus 1. Then this means that we exchange n with n plus 1, and then we put into the equations, which is going to be n plus 6. And from this one, we can take the comparison and compare these two. And of course, we can say that this is true, right? This is true. Because we can write this in terms of n plus 1 and n plus 5, right? So an, or the sequence that is 3 over n plus 5 is decreasing. Decreasing for all n equal or greater 1. Maybe the complete question, maybe the other one, show that an equal n over n squared plus 1 is decreasing. To show that the sequence is decreasing, first we need to make sure that the an is greater than an plus 1. Right? We need to show this. So what we are going to do is we are going to make some comparison, and let's say we can exchange all n, become n plus 1. Okay. And we need to show that this is true. Okay. So we need to solve and prove that our comparison is true. Okay, let's say we can multiply and let's solve this and see what this looks like. This will be squared plus 2n plus 1. And then we can solve this. We can cancel this. Okay, and then we can see that this equation is appearing, and I think since n is start from 1, right? Since n is equal or greater 1, then the equations is true, right? So, or therefore, an is greater than an plus 1, and the an is decreasing. Anyway, as long as you can prove that the statement is true or not, you can always make some conclusions, okay? And then you can write down that the sequence is decreasing or increasing if the question is asking the other way around. And why we need to know the behavior of the sequence, because one of the definition later that define the convergent will be depends on whether the functions or the sequence is monotonic or not. And after we know that it is monotonic, we need to know whether it's bounded or not, okay? Whether it is going to have some restriction on some value or not. And that is the definition for the bounded. Let me write some definitions first. So a sequence is bounded above. Okay, let me write bounded above. If there is a number m such that the sequence is always less than m for all n greater or equal 1. It's similar to what we did in precise definition. So there is another number that is still higher than our an. So if we take increasing the n, and then it will maybe going to reach some value of that m, and it will always stays like that, it means that it will be converges. We can say it's converges to that value, right? Or it's getting closer to that m, right? And of course, this is, if you imagine this in terms of visuals, is maybe going to be like this. And maybe there is some value here that this is the m, right? Okay. We can think like this in visual. I think better if we use the visuals to imagine. And the other one, of course, it's bounded below. If there is a number, let me write with small m, number m, that is m always less equal an for all n and if the sequence is bounded above and below, then it is called the bounded sequence. And for the bounded below, you can look on maybe like this, and maybe there will be some m, small m here. Let me write some conclusion and then we can have a short break, okay? So conclusions, every bounded monotonic sequence is convergent. Which means that sequence that increasing, let me write, an increasing and bounded above. And we say it's converges, and an decreasing and bounded below, and it's also converges. Okay, and I think we can have some short break. Okay, any questions on the previous one, the previous content? Okay, I think if you're still confused on what's really happening in precise definition, later I will give you maybe additional video to be analyzed. Okay, but the point is, precise definition of limit is it doesn't really affect any calculations, right? It's just to show or prove some small numbers, okay, that is nearby the x-axis or the y-axis that is relevant to the limit concept. So it doesn't really affect it any method you are using, like any calculation in limit. It's just to prove that there exists like a small numbers in between some intervals. Okay, that's just the precise definition of limit. If you're still confused, then I think it's normal if you're still confused, because it's such. I would like to rephrase, maybe a little bit abstract, because you don't really compute anything, right? But you can compute the limit, right? You can compute, you can direct substitute, you can use L'Hopital rule, etc., right? It doesn't affect all the calculation you have, okay, for precise definition. And other thing that is important is this monotonic and bounded sequence. Okay, the monotonic and bounded. So monotonic means that functions or sequence will be increasing or decreasing. Okay, you can have two, and you can prove that in some way. If you can prove that the first term is less than the second term or greater than the second term, you can think that maybe it's increasing or decreasing. And then if you know that the function or the sequence is bounded to some value, either above or below when the function increasing or decreasing, you can immediately conclude that it will be a converge or convergent. The sequence will be converged to some value. Okay? So whenever you find a sequence and you can prove that the sequence may be decreasing and then bounded to some value, you can conclude that it will converge. Okay. The same way, if you have a sequence that is increasing and then it's bounded above, and you will know that it will be a convergence, okay, or convergent sequence. Okay. And that's it for the 11.1 point 1, this is the first part, it's up until here. The next part we will go into the series, okay? But that will be next week. Right? Now I will just go some overview on chapter 10, maybe just giving you some practice and to see whether you are familiar with the questions or not. Okay? Let's start from, did I take the picture? Check. Let me start a little bit random. Maybe the one from the textbook first. Yeah. Okay, maybe this one first. This is the polar curves. Okay, maybe polar curves first. So first is, you already have the picture, so no need to draw or sketch. What you need to compute is, first is the length of the curve, and the second is the area. So both questions, it will ask you to use some integrations, and in doing so, you need to have some numbers as your starting point and your end point, right? Okay, notice that the curve, it has equations theta over 2, okay, in the functions. In some way it will be related to, maybe in some cases you need to have some double angle formula to maybe simplify your answer. And if you still remember, this is cardioid, right? Cardioid. So if you want to rewrite the curve or the functions, you can use the double angle formula if you want to look more details. Let me write here. Maybe let me write with alpha first to make sure the general formula. So it will be 2 cosine squared alpha will be 1 plus cos 2 alpha. So this is should be 1 plus cos theta, right? 1 plus cos theta. So if you want to rewrite and then compute, it will be, I think, in some way maybe helpful, right? Anyone find the answer? I think it seems, from what I found, some questions in our calculus 2 it's much more complex and advanced, right? So I think we can, maybe I can let you use the calculator on the exam. Okay. But still, the process on your answers need to be considered more, really, rather than only the answer. Right? So please write clearly the process or some arguments if you have some proof or maybe some steps that you need to provide. Okay. Okay, anyone have done? You can check the calculator, or even you can check using some website if you want. I think you can use Wolfram Alpha if you have. Or maybe if you're familiar with MATLAB, then you can write down in a matrix form. I think it's also okay. Everybody have calculator, right?
Yes.
Okay. And he also used in physics and also chemistry. So
它只是会讲就是地形。我写。是，他只在这个地方。
Or minus something, right? Or
散发两个去让水域散在块，炸草，葱很壮，很丑。我现在就把它试。那我现在直接用脑袋给你，你现在口上也可以到，口上加口上。
Writing the general formula, I think I need to write the general formula. Okay, so for the arc length, let me just write the formula for arc length first. In polar, the arc length can be written as r squared plus dr over d theta squared and d theta. And this will be maybe alpha, beta, or maybe theta 1, theta 2 also okay. All right. And from this picture, if we just want to calculate on the blue line, it means that we are compute from this angle to this one, right? From theta pi over 2, let me just write right here, theta equal pi over 2 to theta equal pi, right? So basically, we can write the L is from pi over 2 to pi, and right inside here the formulations, which is you can choose which one you are preferring. Okay. Let me just choose the original one. Okay, the original one before we choose 1 plus cos. We write r squared as 2 cosine squared theta over 2 and then squared. Let me take this a little bit longer. And then dr over d theta, if we take this, this will be minus 2 sine theta over 2 and then cos theta over 2, right? So we can take this and then squared. So, but let me just plus and then write the results here. And then squared and then d theta. Then one by one we can take this. 2 becomes 4 cosine with power of 4 theta over 2 plus this was minus 2 4, right? Squared is 4 sine squared and then cos squared and then d theta. Let's factorize this cos, okay? Cos squared outside. Cos squared we can write 2 cosine theta over 2. Or if you want to make sure that this is positive, we can take the absolute value, but if you remove also fine, I think. And then take this cosine squared theta over 2 plus sine squared theta over 2. This will be equal 1, right? So this will be equal with cosine theta over 2 will be sine if we integrate, right? But since we have half, then this will be multiplied by 2. So 4 sine theta over 2, and then from pi over 2 to 2 pi. So this means that it's 4 sine pi over 2 is 1, so it's 4 minus pi over 4, right? Pi over 4 means 4 multiplied with 1 over square root of 2, or this should be 4 minus 2 square root of 2. Right? This means that 2, right? 2 square root of 2. I think you could do the same way with 1 plus cosine. Okay. But later, I think at the end, you will have square root 2 plus 2 cosine theta, right? You can change to double angle, half angle, and having the sum squared, right? Sum squared. You have like cos squared something theta over 2, right? And then you can cancel with the square root. And I think the same answer will be appear. Okay, so some important tips for you. If you have maybe square root something, and inside is having maybe 2 plus 2 cos theta, like this one, you can think to using the, always remember this. This is your help. Either cos or sine, depends on the situations. You can always go back to the half angle, and then by using the square from the half angle, you can remove the square root, right? Okay, some tips. Okay. Okay, the number 2, the area. I think the area much more direct. We can use the sector. Let me just erase this. So area will be from pi over 2 to pi. And then always remember, okay, in every polar curve, your area should be equal with half r squared d theta. Okay, the sector, like the sector in the circle. Okay, now if we put directly the equations for the r, 2 cosine squared theta over 2, and then squared d theta. Well, we squared this, it will be 4 cosine with power of 4. Actually, you can have several times half angle from, or double angle from there, but I think for this case, I would prefer the 1 plus cosine theta to be put in the equations. Okay, because it will have more shortcut there rather than the cosine with power of 4. Okay. So let me write half outside, and then 1 plus cos theta, and then squared. And then this will be 1 plus 2 cosine theta plus cosine squared theta. We are just focus only one that we need to take into double angle, right? So 1 plus 2 cosine theta, and cos squared theta I will write plus half 1 plus cos 2 theta, the double angle. And then whole formula multiplied with d theta. And then we can integrate one by one. This is half theta plus 2 sine theta plus half theta plus sine 2 theta over 2. And then from pi over 2 to pi. Then you can carefully calculate this one by one. Well, I think I can write this. Oh, this become 3 over 2, right? Okay. And if in the exam, if you write until here is already maybe 70 to 8, maybe 80%, already 80%. And if you compute and it's correct, then it can be 100. So 80 to 90 is maybe probably this will be 80 to 90%. This will equal half 3 over 4 pi, right? 3 over 4 pi. Because 3 over 2 minus half. And then the other one is 0. So minus the minus 2. Minus half. Yeah. I think minus 2, right? Okay. Okay, let me check the question. Okay, let me go through the second questions. Okay. let me start from the tangent. Okay, find equation of tangent to the curve x is equal cosine theta plus cosine 2 theta, or t in parametric, y equals sine t plus sine 2t at t equal pi over 2. So you need to find the tangent line. Okay, I think you can directly get the answer, right? So writing dy over dx for the slope, so slope will be dy over dt over dx. And based from what we get from the information, this will be cosine t plus 2 cosine 2t. And then this will be minus sine, and then minus 2 sine 2t. And we input t equal pi over 2. Pi over 2, this will be minus 2, right? Because this is 0, this is minus 2. The other one will be minus 1, minus 2, minus 1, right? Minus 1. 0 here. So we will have 2. Then we can take the y at y pi over 2. This will be sine pi over 2 sine pi. So x pi over 2 0, and cos pi is negative 1, right? So we can take the equations y minus 1 equal to x plus 1, right? So y equal to x plus 2 plus 1 plus 3. Okay. Okay. I think we can take one more question. One more question. Let me write here. Find the area of region that lies outside the circle r equal half and inside 4-leaf rows r equal cosine 2 theta. So you have two polar curves. The first one is a circle with the radius half, and the other one is the rose curve. Okay. Just the curve that I think we already mentioned in the polar coordinates and the polar curves. So we need to find the area. Okay, it lies outside the circle but inside the rows. Let me give you a few minutes to try. So first you can sketch if you want, but if you want to directly going to be approaching the equations, you might find the intersection first. Find the intersection first, and make sure the angle. And at least you have some endpoints. remember that if you have the rose curve like this, it is having symmetry, right? Symmetry. So you can take that as you can multiply with. So you can maybe from 0 to something, and then you can multiply with the number of the roses, number of the area. Maybe I can help you with the drawing. Okay. Let me give you the drawing here. Maybe that is our curves, and then we need to define our area that is mentioned in the questions. So lies outside of the circle but inside of the roses. So it should be this one, right? The yellow one. Okay. So at least, if we know at least this angle here, we can take the angle from 0 to here and then multiply with 1, 2, 3, 4, 5, 6, 7, 8. Got it? Okay. So first, let's just check the intersection. So intersection, we might use the half and cosine 2 theta. So we get that the theta at least is going to have some pi over 6, right? At least from 0 to 2, from 0 to some pi over 4 here, it will be having some pi over 6. So at least theta on this section here, that will be theta equal pi over 6. Okay. So how do we compute? So integrating from 0 to pi over 6, and then the curves will be the rows minus the circle. Okay, got it? Okay, you need to be careful on the polar curve, because sometimes the problem that the student might have is if they mix up the polar with the Cartesian. Okay. Remember, in polar, if we want to evaluate the area, you need to imagine how your point will move. So you move from 0 and you move here. Okay. That's how you determine which angle you want to use. Okay. So if I want to put my hand here, this means I start from 0 and then move here, and this will be pi over 6. Okay. So that means that this is what I want to evaluate. But since we have this is the rows and this is the circle, this means that the integration from 0 to pi over 6 of the rows minus the integration from 0 to pi over 6 of the circle. Okay, so let me write that for you. Let me take this as A1. Okay? A1 will be 0 to pi over 6, and then the formula is the same, half r squared. Okay? So this will be, let me write, let's say R2 for the rows, okay, minus R1. Let's say this is the circle. So this is rows, this is circle. Okay. So we can write the A1 here. This is cos squared 2 theta minus one over 4. Or maybe I will write directly to multiply with 8 times. Okay, so because this is having, due to symmetry, we can write the total area will be 8 multiplied by 0, integration from 0 to pi over 6, half, and then this will be cos squared 2 theta minus 1 over 4 d theta, and this will be a equal 4, and we can integrate 1 by 1, and then using the double angle formula, we can take this 1 over 4 plus half cosine 4 theta and then d theta, and then this will turns out to be pi over 6 plus half sine 4 theta. Or this should be 4 over 6, pi over 6 plus square root of 3 over 4. Okay, I'm skipping some process, but should be the same result. Should be the same result. Should be, if you confuse here, this should be this means that I'm directly canceling the 4 from the this 4 here, and from sine over 4 from 4 here, so cancel. I think that's it. That is for today, and maybe this week maybe I'm giving you more, maybe some additional content, but I think it depends. Okay, it depends.